Playing the pedal steel guitar takes quite a lot of skill. You slide a steel bar up and down the strings as you pluck them, all the while operating a system of pedals and knee levers below. This means using both hands, both feet, and both knees. But a pedal steel guitar's unique sound and impressive range are worth all the effort. To make one, a guitar maker first carves the neck of the instrument from hardwood. He beads glue around the edges of the neck and applies strips of intricate wooden inlay. Once the fretboard design is silk-screened onto the top, the guitar neck is complete. The guitar maker then outlines a design onto aircraft-grade aluminum and cuts it out to make an end plate for the guitar frame. He pops the end plate out of the holding device. Then, he welds it to the rest of the framework and polishes everything to a mere finish. Next, the part of the guitar called the steps is machined. The holes in the steps will be used to attach tuning pegs. There's one for every string. The steps are attached to the neck just above the fretboard. This is the pickup plate. It will hold the device that transfers sound to the amplifier, as well as a series of metal fingers. The fingers are made from several aluminum pieces that are machined and assembled together. The fingers pivot to raise and lower the pitch of the strings. All of the fingers are fitted into the pickup plate and secured with screws. The guitar maker double-checks the fingers' movement. Then he hooks springs to the end of each one to maintain the proper tension. A little grease ensures that this next step goes smoothly, the production of the guitar's cross shafts. Then, it's onto the guitar's undercarriage and the system of foot pedals and knee levers that will move the fingers. The guitar maker screws several cross shafts, one for each pedal, into the undercarriage. He attaches bell cranks to the cross shafts, then connects thin steel rods from the fingers to the bell cranks. This system will allow the performer to tighten or relax strings while playing, which gives the instrument its characteristic sound. The guitar maker tests the knee lever. Here, he's winding copper-coated wire around a cartridge thousands of times to make the guitar's pickup, which transfers sound from the guitar to the amplifier. He takes two of the wire-bound cartridges and places a magnet between them to complete the pickup. Then, he fits it into the other slot in the pickup plate, just above the fingers. Now, using a gauge and a level, he adjusts the pickup. It has to sit low enough in the slot that it won't interfere with the strings. There's no room for error here. The positioning must be exact, or the guitar won't sound right. Ten to 12 strings are attached to the guitar neck. Some instruments have two necks to add even more dimension to the sound.
Piano keys were once made out of ivory. This sought-after material isn't used anymore because it's banned to protect elephants who were killed for their ivory tusks. Pianists now play plastic keys, but the techniques involved in manufacturing a piano haven't changed much and still rely on hand craftsmanship, just like a century ago. Beautiful music is a triumph, but so is the piano itself. Made of inner and outer rims, a soundboard, treble and bass bridges over which the strings are stretched, and a heavy cast iron plate. To make a piano rim, automated rollers spread glue onto sheets of hard rock maple, coating both sides. Then they layer the glue-soaked sheets 5 to 8 deep, depending on the model of piano. Workers feed the wet layers of wood to a rim press. An impact wrench powered by compressed air turns the clamp screws. The screws bend the wood into a piano rim form. They measure the pressure on the layers with a torque wrench. Steel arms reach across the wood, holding the shape while the glue dries. After 24 hours, workers loosen the machine's grip, and the rim now holds its contour. Now it's into what's called the conditioning room for more drying out. The piano rims stay in this warm, arid room for 30 days. It's time to make the bracing structure. They place glued struts inside the rim, then apply pressure with a clamp. The framework remains in this embrace for an hour while the glue dries. This piano will have a tension resonator for extra support. Steel turnbuckles attached to a center hub. A worker tightens the turnbuckles with a wrench. Then he thumps it to make sure it's tight and won't rattle. Next, they'll install the soundboard made of spruce and the 2 bridges. Strings will straddle the bridges and transmit vibrations to the soundboard, which is the amplifier of the piano. A worker glues ribs onto the soundboard. He lowers wooden clamps over each rib to apply pressure while the glue dries. That takes about an hour. Next, he thins the ribs around the edges with an automated stagger tooth shaper cutter. This will allow the soundboard to resonate freely when the piano is played. Now they position the soundboard in a bridge press. Then they place a bridge locating fixture on top of the soundboard. This device holds the bridge in place while it's glued to the soundboard. After the 2 bridges are glued down, they lower the soundboard onto the piano rim. Then they hoist a cast iron plate onto it. It's a critical fitting. If they don't get it right, the piano will never function properly. Then the plate is removed for finishing. A worker cuts notches in the bridges, which are now topped with a lubricant. This very sharp chisel cuts through the hard maple like butter. Each notch will cradle 3 piano strings, giving them the freedom to vibrate. Now they roll glue onto the outside case of the piano, which is made of rosewood veneer on maple. They fit it snugly over the rim structure. A mechanical clamp holds it in place for an hour while it dries. Then they stand the entire piano on its side. Spinning cutters shape the arms that sit next to the keyboard into an elegant curve. This is called a vertical stroke sander. A worker runs it along the side of the piano to smooth out the wood. After a black polyester paint is applied, they buff it up with this electrical cloth polisher. Then they hand rub a mirror glaze cream into it until you can really see yourself in this half-finished piano. The bass and treble bridges are now fixed to the soundboard of this half-finished piano. Then, to add glamour, they spray gold paint on the cast iron plate. The next step involves the pin block, which holds all the stress. It bears 45,000 pounds of tension from the strings and transfers it to the iron plate. He drills into the maple pin block through holes in the iron plate over it. The holes are for the tuning pins, hence the name pin block. They unfurl pieces of steel wire from big coils. Using a vice grip, the worker twists the end of the wire into a neat loop. Then he hooks it onto a hitch pin on the back side of one of the bridges, making sure it runs between the guideposts over the bridge. Now he threads the wires through another guide called an agraffe. Using wire cutters, he snips the wire to the exact length that he needs. Then he wraps the wire on the tuning pin using a device called a stringing crank. He taps it into a hole in the pin block. Then, using a pneumatic hammer, he drives the tuning pins into the pin block. Now the string stretches from above the bridge to the pin block. Each string is under a tension of up to 425 pounds. Again, a force that will be kept in check by the heavy cast iron plate. Now he places little felt-covered blocks called dampers above the strings to stop them from vibrating when a note is played. Using pliers, he makes parallel bends in the damper wires so they're aligned. He pounds the keyframe, checking for gaps that could cause knocks under a pianist's vigorous blows. He smooths out the gaps, shaving off bits of wood with a strip of sandpaper attached to a handle. Now another worker presses the piano keys in between steel guide pins that have been installed in rows on the keyframe. She uses an air cylinder to push the back check into the end of a piano key. The back check is a piece of wood covered with felt and buckskin that will catch the piano's hammer after it strikes a string. It's time to make those hammers. She glues the felt-covered top onto a thin piece of hornbeam, a species of very strong wood. When a pianist hits a key, it will catapult the hammer into the string, and that produces a note. Now she aligns the hammers to be perfectly parallel, using a plastic square as a guide. This is called squaring it up. Next, she sands the tail of each hammer with a file, so there will be no sharp edges to damage the back check. Then she attaches the hammers to the top of the keyboard with screws. Now she places weights on each key, and then gently taps the rail to get the hammers moving. She's testing the amount of effort it would take for a pianist to push each key down. This is called the weigh-off. After she determines how much weight is needed, she marks a place on the side of the key and drills 1 or 2 holes. She plugs each hole with a piece of lead. In a process called swedging, she pushes a divot into the lead so it expands and fits snugly into the key. The lead will counterbalance the weight of the hammers and give the key the required amount of weight. Next, this technician checks each hammer in each key, making subtle mechanical adjustments so they move smoothly and fluidly. It's the piano's first big tune-up. He fine-tunes the hammer action by using a let-off tool to adjust the driving mechanism. The piano is now ready for the hands of a skilled pianist and the ears of an appreciative audience. The music it makes is as complex as it is majestic. The pipe organ is one of the largest and most technically sophisticated instruments. Building one is an incredible feat of engineering and craftsmanship. Early man discovered he could make music by blowing across hollow reeds of different lengths. In ancient Egypt, An engineer devised what later would become the basic technology of the pipe organ, a steady airflow without mouth blowing, while controlling the air to each pipe to create different notes. By the Middle Ages, the pipe organ was a fixture in churches throughout Europe. Johann Sebastian Bach composed his greatest works for organ while working as a musical director of a church. A concept artist creates the design. The design then goes to a draftsperson, who prepares the technical drawings. The organ's pipes are made of a mixture of tin and lead. Tin, the harder metal, gives brightness to the sound, while lead, the softer metal, gives it warmth. Artisans pour the molten alloy into a tray, then draw it out to form a sheet. As the sheet cools, the two metals react to each other, creating spots. The sheet goes into storage to give the alloy time to stabilize. 2 to 3 months later, it's ready to be formed into organ pipes. First, they cut pieces of metal in the shape of each pipe, using templates and large rulers. Then they roll each piece using a mandrel. The larger the organ, the more pipes it has. Pipes are grounded in sets of 61, corresponding to the 61 black and white keys on the keyboard. An elaborate organ can have more than 10,000 pipes. The pipe maker carefully seals the body of each pipe by hand using tin solder. Next, he solders the body of the pipe to the foot and languid. The languid is the part that produces the pipe sound. The process of giving a specific sound to each pipe is called voicing. This work is done by a trained musician called a voicer. He enlarges the mouth of the pipe, called the cut-up, until it's approximately 1/4 of the width across. He adjusts the pipe some more, blowing air through it to judge how to further refine the tone. Next come the wind chests, also called the soundboards. These are the large wooden boxes filled with air on which the pipes stand. Under each pipe is an air channel covered by a valve. The valve is made of leather and sits on a wooden board. When the organist pushes a key on the keyboard, the corresponding valve drops down like a trapdoor, releasing air into the pipe to play the note. They glue the valves to the wind chest one at a time using animal glue. It's suppler and dries faster than synthetic glue. The valves are connected to the organ's keys mechanically, by long tracks of cedar wood or by electrical wiring. The electric signal triggers electromagnets to cause a sudden air depression, making the trapdoor valve drop down and let the air in. The console is the organ's brain. It contains all the controls for the keys and sets of pipes. The organ's white keys are made of lindenwood, covered with bone. The black keys of ebony or rosewood. An artisan adjusts the keys using a weight. When the weight rises, the tension is just right. The console, keys, and all the other components are finally put together in the assembly room. After testing, they disassemble the organ and ship it to its destination, where it's reassembled. The voicers come on site to perform what's called tonal finishing. They check and adjust each pipe according to the acoustics of the room. This process can take many months for a large and elaborate organ. Today on How It's Made. Plastic injection molds. Automotive oil filters. Filing cabinets. And blown glass. If you take a closer look at the products around you, you'll notice that many are made of parts that have been assembled together. One way factories make product parts is by melting materials such as metal, rubber, or plastic, then pouring or injecting them into molds. To make a plastic part for a product, the manufacturer has to first commission a mold-making company to design and produce a plastic injection mold. The mold begins as bars of chromium steel, a highly durable metal that can withstand repeated high-pressure injection of plastic. Workers assemble several bars into a block called a mold base. They mount this base on a milling machine, which shaves the bars to the right dimension. This step is critical, enabling them to later machine the base into a mold that's true to the technical design, right down to the 100th of a millimeter. A mold usually consists of two halves, each of which is comprised of several components. The factory drills strategically positioned holes in each base for the guide pins and bushings that hold the components together when the plastic's injected. A grinder now goes to work smoothing and leveling all surfaces. This prepares the base for the high-precision machining operations that will transform it into a mold component. A computer-guided tooling machine called the CNC slowly machines the base, wearing away the steel particle by particle to create the mold component shape. This one, part of a mold for the plastic rim around a snowmobile's front headlight, takes 20 hours to complete. From here, most mold components go on to a second tooling machine, especially if they require fine detailing that this CNC machine isn't capable of carving. The second machine is outfitted with a copper electrode in the shape of the plastic part, in this case, a snowmobile oil gauge. After polishing the electrode to ensure flawless casting, they use a sophisticated measuring device to verify the dimensions. The electrode goes face down on the second tooling machine called the EDM. Directly underneath is the mold half that's been partially formed on the first machine. A strong electric current runs through the electrode and penetrates the mold, forming a cavity in the shape of the electrode. After tooling, they drill coolant lines. This is for the cooling fluid they'll use to accelerate the hardening of the molten plastic. Some plastic product parts, like that snowmobile oil gauge we saw earlier, have lettering on them. The factory engraves the letters in reverse inside the mold cavity. After the plastic's injected, the writing is right side out and raised. The surface of the mold cavity is pretty rough from all that tooling, so they polish it smooth to ensure proper casting. Here's what the two halves of a finished mold look like. The pins and bushings fit together to close the mold before injecting the hot liquid plastic. Once the plastic cools and hardens, it's just a matter of extracting the molded plastic part. Here's a different molding method. A two-step process they're using to make buttons that go on the steering handle of a jet ski. First, they mold a structural base out of hard white plastic. Then they put the base into a second mold and inject a rubber-like gray plastic. This softer plastic covers everything but the raised lettering, giving the button a softer feel. Factories also make molds for aluminum injection and rubber injection, among other materials. They build those molds from different types of metal, but using the same techniques.
Pliers date back to around 2000 BC. Ancient drawings show Greek gods with pliers at the forge. Today, forgers still make pliers, but these days, they use automated tools to shape the metal. Without them, a lot of electricians, plumbers, and mechanics would be out of a job. Pliers have three basic parts: handles, a rivet, and jaws. All the parts are made from steel that metal workers forge into shape. First, a powerful electric furnace heats the steel red hot in just a few seconds. Then, a metal worker sets one sizzling rod at a time on a forming die. A massive die forger hammers the rod against the die with tons of force. It takes up to 4 strikes on separate impressions for the rod to acquire the die's shape. Then the forging is placed onto a press that trims off any excess steel. Two forged rods are needed to make one pair of pliers. This pair will be for gripping, so the next step is to machine the teeth into the jaws. Workers set the plier halves into the broaching machine. Its tiny cutters, dozens of them, shave away steel under a shower of lubricant. When the cutters pull away, the jaw of each plier half now has a nice set of teeth. The factory must heat treat the steel to harden it, a process called austempering. The plier halves travel through a gas-fired furnace for about 2 hours at a blazing 1500 degrees. Then, the steel is dunked in salt water to cool rapidly and evenly. The teeth on these pliers will have to take a lot of abuse, so they get a laser heat treatment to make them even harder and more durable. Now the pliers are ready for assembly. For gripping pliers, a worker inserts a single piece rivet and joins the two halves. He then sets the joint onto a machine that spins at high speed, generating the force and friction needed to set the rivet. Cutting pliers are also held together with a rivet, but the setting process is different. The parts go into a press that applies both heat and pressure to secure the rivet firmly. Next, workers insert the cutting pliers between 2 stone grinding wheels. Again, lubricant prevents the steel from overheating as the wheels wear down the rivet until it lies flush with the plier surface. The cutting pliers go into a gas oven for another 2 hours of heat treating, a process called mar tempering. When they come out, they cool in an oil solution, rather than the salt solution that cools the gripping pliers. Steel is a finicky material, so it's critical to manage the heat treating process meticulously. Otherwise, the metal will be substandard. After heat treating, the pliers go into a bath of rust inhibitor that helps protect the steel from corrosion and lubricates the riveted joints. A robotic arm runs one pair of pliers at a time against a grinding belt, polishing all surfaces except the handles for a sleek finish. Then a laser engraves the company logo and product number. Automated bars now lower hundreds of pliers handle deep into a tank containing liquid vinyl. No messy drips here. Before dipping, the factory heats the pliers to help this coating stick to the steel. Next, the pliers go into an oven. The heat hardens the protective coating, cushioning the handles so they're easier on the hands. Whatever their shape or size, pliers are a toolbox essential for anyone looking to ply their trade.